Hello, this is Dr. Lori. Welcome to this next video on the critical ratio. And what I'd like to start with is what I call the eyeball method. And I think the eye does a pretty good job of really understanding hypothesis testing. With the eyeball method, we don't get specific numbers, but we can see sort of the gist of what we're trying to evaluate. So what I want you to imagine is that we have these three sampling distributions of the mean, all three of these over here, 1, 2, 3. Um, and let's just imagine, if you would with me, that we would like to, we're looking at the 95% confidence interval, so out here in the tails, this is outside of that 95%, and everything in between is within the 95% confidence interval of the mean. We could do that for all of these, and we'll make these two more or less equal. We'll just follow this down. And then this one's quite a bit narrower. And so here we have that little 2.5% and another little 2.5% over here. But here's our 95% confidence interval. You'll notice that all three of these sampling distributions of the mean are located at the same place. So they're intended to have the same mean along the scale of whatever continuous variable we're measuring. So here's our mean of the x bars. Again, same thing. And what we'd like to do is have three different scenarios where we're looking at whether it's reasonable that our sample mean of the distribution means is equal to a certain value. So let's just imagine our population mean for this first one is out here somewhere. So here's however far away that is, and I haven't designated the scale. That's not relevant for this particular discussion. But that looks, here's our mean, that looks really far away. The farther away, the more likely that that is caused by more than just random variability. In this second scenario, let's imagine that instead of being way over here, then we're evaluating whether this mean of the sample means is different from, let's say, a population mean that falls right here. And you can see that it's not as far away. It is closer. So the distance here, let's get a different color. The distance from here to here is quite a bit wider than the distance from here to here. So distance matters. But then I'd also like to point out that one other thing matters. And if we took this same population mean and tested it against a different sample, the distance here is the same as the distance in this particular scenario. However, in this case, it seems a lot more like this first scenario where we're way out here in the tail. We're certainly past that where it kind of transitions outside of the 95% confidence interval. So there are actually two things going on here. It's the distance they are apart, but then it's also how far the actual distribution itself is spread out. And so what I like to say is that both location and spread. So the location of our mu sub x bars is relevant, but then also how far spread out those sample means are, the sampling distribution of the mean. Both of those things really come into play. So when we're calculating something called the critical ratio, we actually do that same exact thing that you did with your eyeball, except we calculate it with numbers. And so I'll give you an example of what's called a t-test. So the t-value is equal to the distance between the means. In other words, how far it is from here to here. Here we have a much smaller distance. Here we have that same small distance. But it's that distance between the means divided by the variation around the means. So in other words, how far this actual distribution is spread out. That also matters. This one is spread out, but just not as wide. So this 95% confidence interval is quite a bit narrower than this one is. And so I like to think of this as the location divided by how spread out it is. And specifically for a t-test, the t is equal to x bar minus mu. So in other words, here's our x bar, here's our mu. How far apart are they spread out? Divided by the standard error. Now here's this whole notion of the standard error coming into play again. As you recall, as our sample size goes up, so as increase in n, that definitely impacts our standard error. Standard error gets smaller and smaller and smaller, and this confidence interval gets narrower and narrower and narrower. So with the same distance between x bar and mu, see how this one has the same distance between those? This one looks like it's outside of that 95% confidence interval, and that's because it probably, if all other things were equal, if the sample size was larger, then that standard error gets narrower and narrower and narrower, the 2 times the standard error. So we keep seeing that concept over and over again. The other thing to remember about this, or to think about, is the whole notion of tails. All this time that we've been talking, we've talked about something where we have 2 tails. And so here's evenly distributed on both sides. So the norm is 2 tails within almost all of the published literature. But it is possible to have what's called a one-tailed test. And basically what we do with a one-tailed test is we take this 2.5% that really started out in the two-tailed test over on one side, and we put it all in the other side over here. So what that does is, instead of being my 95% confidence interval being cut off at the 1.96, it moves that down to 1.64. So then 1.64 times the standard error, and the reason for that is because then everything below this point, including the tail all the way out to however far it goes, that now is my new 95%. And so really, when we're doing 95%, the other 5% needs to be up here at the top if we have just a one-tailed test. So I hope that kind of makes sense conceptually. You'll almost never do a one-tailed test in actual practice, but it's good to understand how that works. Thanks for joining me for this discussion about the critical ratio, T.